In today's lecture, we are talking about design, and we have a second lecture about CAD and 3D printing. So, starting from wait, hold on. Starting from today, you will be making your design, and then uh, you will start from there. Once you have something, you will see the performance, and usually, if the performance is not well, you will have a new design. So the initial concept for design is important. If you make a wrong decision, maybe the entire design process will take a long time. Now, for today, I prepare a PowerPoint. I want to share with you how I vision design. So usually, you need to think about the future. If you don't have the idea of the future of the things you need to do, then you are just it's like you're blind. You don't know what you are going to do later. So I will recommend you to understand about something related to my lecture, and then I hope this information will be helpful for you. Let me. Okay. So uh, I want to talk about something called design optimization. Um, Usually, optimization is done at the end. Let me take design of this table as an example. Let's say I'm the engineer who designed this table. If I want to sell this table, I will make CAD drawings, and I can guarantee you this is not the initial design. There are multiple versions. So how come at the end this is the final product? Who make the decision? If I am the manufacturer of this table, I need to know about something, how to make a mechanical design. Even for chemical or material science, you need to know what to do. So take a look at this table. There are dimensions to make, like width, length, thickness of the table of the plate right here, and also the material I use, the coating on the top, and the body. The body has a design. Do I want I want the chair and the table to be linked together. There are so many things to make decisions for. So it's very challenging. So usually you need to narrow down what you want to do. You probably have to uh, make something fixed. For example, maybe as a manufacturer, I decide the chair and the table has to be fixed, and then I decide I plan not to do nothing. I just want to make sure, no matter how strong a person is or what's the weight of the person, when I sit on this table, on this chair, it won't break. Or if, like myself, I'm not 100 kilogram, if I sit right here, it won't break. So there is an issue about the strength of this product. Or if I only just focus on the strength, then probably something else is fixed. So I need to figure out what is the most critical part for design for strength. Do I talk about a scenario where a person may sit on the table? Or do I just talk about a person who just normally sit on the chair? So you need to set up scenarios. So whenever you set up scenarios, you can then convert this problem into a simple engineering problems. We all learn about basic physics. So it becomes a physical problem. You can formulate a problem with some vectors, values. You can solve for force balance. Even you are in the material science field, you know how to do force balance, right? Then you have math equations, and you want to satisfy certain math equations. And usually, when you change the design parameter, the performance changes. In our discussion for the strength of this table, that would be the main topic that we talk about. So we want to focus on that. And maybe something else are just regular rules that we satisfy. So in this, and also we focus on, okay, which would be the important parameter. Okay, so I would say I will take this one as the example again. I want to make sure the structure is strong enough. So I want the strength to be as large as possible. Maybe that's one thing I can do. So strength, higher the better. Okay, higher the better. Okay. So if I want the strength to be higher the better, what would be the design parameter I choose? After a quick observation, I noticed there is a round dimension here. Okay. Why does the engineer choose this corner to be round, not a straight corner? Because when the structure is carrying load, round shape tend to distribute the force. So the structure can share the loading. If it's a straight corner, usually the force concentrate at the corner, so the corner can break easily. But how large should I choose the radius? So maybe I can use the radius and try different small ones or big ones, but I don't know. I don't know which one is good. So this is something I can change. This is something I want larger the better. And maybe there's something else. So definitely, if I choose this radius as my control parameter, there usually is a guideline for the radius. For example, there is never a negative radius. So radius has to be positive, right? It's impossible to have negative radius. And also, maybe radius has to be smaller than some number, maybe 30. I cannot build a corner like that with a radius of infinity, right? So there's usually some limits. So if you have this kind of mindset in a design, then you can know what to do. And actually, from here, you can already do optimization. So I want to teach you what is optimization in today's lecture. And later on, when you make designs, probably you need to make a guess. Maybe the thickness of the soft robot at certain point, or like a thickness of the air chamber can be an important parameter. Thicker, probably something will happen. Thinner, probably something will happen. It's impossible to have zero thickness. Maybe 1 millimeter thick is also impossible. You probably has a lower value, smallest value that you can produce. For example, the thickness has to be larger than 5 millimeter because any value lower than 5 probably is impossible for you to make. So there are some physical rules or constraints or limitations in your design. You need to realize it and then try to formulate or make a guess what's going to happen. Now, let me show you what is optimization. So I always imagine optimization as skiing, like someone is skiing in a snow mountain. I will explain why. So usually skiing is like you are at the very top of the snow mountain. Who has ever skied before? Anyone? Oh, nice. Anyone from Hokkaido or so? If you have ski in the past, sometimes you are at the very top of the mountain, and then maybe the day is foggy, which means you don't really see very clearly what's going on at the bottom of the mountain. So I imagine solving optimization is like that. You are just moving around inside the snow mountain. You want to stay in the trails that's available for you. You don't want to ski into the woods. Okay, so there's usually some area for you to ski. And what's the goal for skiing? At the end, you go to the right position, take a rest at the center downstairs, not downstairs, down there at the bottom of the mountain, right? So you eventually want to go there. You will not stay on the mountain. Otherwise, when after sunset, no one knows you are still up there, right? So your goal for skiing is to get down the mountain. So over here, if you know about contours, for mountains, when we study the geography of mountains, we can draw contours to represent the height of the mountain, right? So if you can draw the mountains and then draw the height levels into those shapes, then it looks like this. And usually there's an area that has the lowest height. That's the goal. So when we solve optimization, actually, it's like moving along this contour and then trying to go to the lowest place. And that's what we call the optimal solution, actually. So, what is feasible space, feasible domain? So, like I said earlier, when you ski, you don't want to bump into the woods. You get hurt, right? There's an area that you can stay. So, those are I call skiable area or so-called the feasible. So feasible means something that's acceptable. Stay at the acceptable lanes or trails. Do not ski into the rocks or the woods. Okay, so the process of doing optimization usually can be expressed like this. Okay, we have math functions. The blue one is so-called the objective function. And the position of the skiing person is the variable. So when you are skiing, you are like a design point. You are changing your position inside the snow mountain. And when you ski down, the height of your position decreases. You try to decrease the function value to the lowest. But there are some limitation. You don't want to ski into the woods. So we call them constraints, like the limitations. So over here, I did a animation. It's like initially you don't know where is the goal. You ski somewhere from the top of the mountain, and then one person could be skiing following this trail, and he can stop right there. So if the person is still within the feasible region, we call this point as a feasible point. It doesn't violate the constraint or the limitation. It remains inside the feasible space. Or some other person ski and then get onto the wall, stop right there. He didn't go further, stay on the boundary. When a design point is still on the boundary, we still treat it as a feasible point, feasible design. But if another person ski and then he's crazier, he ski outside of the boundary and then bump into the woods, then we call it an infeasible point. Using this table design as an example, if someone decide, hey, let's try radius of 200, how he physically make a engineering drawing and design that radius as a 200 value, then it bump into a very unacceptable design. Then it's violating the rules he decided. So those are called constraints. When you have larger sign or smaller sign or equal sign, you define the rules. You want to make sure your variables satisfy the rules. When the design satisfy the rules, they are feasible. They're okay design, but they may not be the best. So right now over here, this design and this design, this design is inside the feasible space. The other one is on the wall. Those are okay. Those designs are okay, but they are not yet optimal. This design is not good. So usually during the optimization process, we don't want to try the infeasible design. Usually we don't. Now, finally, we want to move the design point through some kind of process and hope at the end it can find the lowest point. So optimization process is like a kind of process that allows you to move the design point along some path and eventually you stop. Okay? So now you need to have the mindset. I'm designing a soft robot. What is my goal? Do I want to maximize the bending angle? Okay. And what do I change? Thickness of the chamber. Okay. When I enlarge the thickness, does the bending angle increase or decrease? So I need to know the relationship between them. Okay, now if I can change the thickness of the wall, of the soft robot wall, is there any limitation? If it's too thin, that cannot be manufactured, or it can break easily. If it's too thick, probably it doesn't bend, it doesn't deform. So there's always a range, okay? And maybe you didn't choose the right design variable. The thickness may not be the best one. Probably it's actually the radius of the corner. So you need to make a decision what would be the design variable. Can you have multiple variables? Yes, you can. But it's harder for you to find a solution. because you are changing too many parameters at the same time. So it takes more effort to figure out what is the best choices for multiple variables. So today I will show you how to do one variable optimization. So here's one simple example. Here is a math function. There are this is a two variable problem. So everyone can easily make a drawing of this function. The 10x1 squared plus 3x2 squared. Can anyone tell me what's the solution if I want to minimize this function? It's very easy. Yes, 0. Actually, 0 and 0. 0, 0. Yes. It's over here because that's where this function is the smallest. You cannot find any other point that gives you even lower value. So that's optimization. If you know the function, find the variable that allows the function value to be the lowest. Okay, how about, yeah, obviously that's the solution. Okay, here's another example. What if I put a wall inside a space? The wall, the rule says I want to make sure x1 is larger than 1. So if you make a drawing of this limitation, it's like a wall right here. And the hash right here represent the left-hand side is so-called the infeasible space. You cannot stay on the left-hand side, but you can do the right-hand side. Okay. Now, what's the solution? Anyone? This is something that you can just observe and then figure out. Anyone? Say again? Yes. So that is the point that is the closest to 0, 0. So if you are not sure, I can make some drawings, then you probably can help you to understand. So earlier, we had a function. I tried to draw contours of the function. So they are contours, right? So contours means whenever on the same curve, they are sharing the same function value. So over here, this function value could be 100. This could be function value of 80. This could be function value of 60, right? So earlier, right at the center, the function value is 0. Now I have drawn a wall and it's tangent to one of the contours. So that means every point on that red contour is still sharing the same function value, and it's also staying on this black wall, right? So you can, if the function value of the red contour right here is 60, that means right here at this point, the function value is still 60, right? Now, how am I sure this is the position with the smallest function value? Let's zoom in. After zoom in, I have a tangent point. Here is function value equals to 0. This point also function value equals to 0. Not 0, 60. If I move a little bit to here, move up, it goes further toward higher value of 60. So I can actually have another contour right here, and this could be the function value of 62. So if you are moving up and down, you actually have higher function value. How about going inward, right here? Yes, if you go left, the function value could be lower, for example, 53. But it violates the wall I have drawn, right? Because I said I need to find a point on the right-hand side of the black wall or on the wall. How about moving right? If I move right, it's the same idea as finding a point, move up or move down, because any point on the right may lie on the contour with a higher function value, maybe 65. So by this observation, you realize that would be the position with the lowest function value. Okay? So another practice. If I have a function, if I now set up a different wall, it's like this. And I said, and I say, stay on the left lower corner of the wall. Okay? Where is the smallest point? From what we have learned in the first example, you realize this tangent point is actually the smallest function value point. Okay? So if you have this kind of sense, it's easy for you to observe where is the minimum point. Okay, let me give you more examples. Here's another example. Now I have a second rule. Not only I need to stay on the right-hand side of the first line, so x1 is larger than 1. How about x2? x2 has to be smaller than -2. So it's a horizontal line and we need to stay at the bottom of it. So now I need to satisfy two lines, two rules. Can anyone tell me what's the solution? I need to stay on the right-hand side of the so from here I gave you some hint. Here is the invisible region, here is invisible, here's invisible. Only the right lower corner is the visible space. What is the point that has the smallest function value inside this region? Should be very obvious. Yes. Yes, you're right. Here, you're right. So sometimes if you can if you know the function, you can make drawings. You don't even need to know any algorithm or methodology. By observation, you probably can see what's the possible solution. Okay? So very good. Thank you. Now, another rule. It's possible. Usually in engineering, we have so many rules. So there's a third rule. This time, please be aware, I'm not having the smaller sign anymore. I'm having equal sign. So if there's a rule says x2 plus 2x2 must equals to 0, then you can make a drawing. It's actually this tilting straight line here. So in order to satisfy all the rules, staying on the right-hand side of the straight black line, staying underneath the horizontal line, also staying on the tilting line, the only feasible point, only feasible space is actually this red line. I need to find a point on this red portion. So can anyone tell me what's the solution? Where can I find a point on this red portion and the function value will be the smallest? Yes. 4 minus 2? 4 minus 2. Yes. That would be the intersection point. Yes. So over here, that would be where you have smallest function value. So I think many of you was able to give me some responses. That means you understand the drawing. I think the drawing can really help when you try to solve optimization. And from here, you can see one thing. When I have three functions, three so-called constraints, in Chinese means 限制. When I have three constraints, two are useful. The first one is no longer useful because it doesn't matter. If I get rid of the first one, it doesn't change the solution. So sometimes if you have too many rules, or if you really have, you must have many rules, some of the rules won't matter. Can you tell from this example? When I have three rules, the first rule doesn't matter. It doesn't change the solution. So it will be better for you to recognize, this rule doesn't matter. I can get rid of it. I can give you 1,000 examples that is a useless rule. Let me show you here. For the table design, I can set up a rule that is not necessary. Radius must be larger than -1. Radius is larger than -2. Radius is smaller than infinity. Radius is smaller than 1,000. All the red rules are not necessary because they are wider than the blue constraints. Why would you set up a rule that is not useful? So when you are in the design process, you define what are the variables. You pick up what's the important function, something you want to enlarge or shrink. You find what are the related rules. And one important thing about the rules, not all of them are important. Okay? So have this mindset. So like over here, if I get rid of this wall, it doesn't matter. Same solution. Okay? Now, sometimes when you have a function, it's complex. Then it's hard for you to find a solution. So today, I'm going to teach you, I think, the first method you will learn in optimization. I hope it will help. Okay, so there are some mathematics. I know mathematics in the first class is very boring, but I hope you can learn something. So before I start, does anyone have ever heard of Newton's method? So what do you know about Newton's method? Linear approximation. Okay, good, very good. That's almost what I want to show you today. Almost. Any other person who has know about Newton's method? He's right. But any other would like to also raise your hand, say something? Okay, so let me remind you, we have learned Newton's method, I don't know when, maybe in calculus. So usually if there's a function, something like this, Newton's method help us find the root. This is called the root, right? Calculus. I think we learned in calculus, right? So Newton's method help us that. Can anyone Tell me how it's done. Maybe not. But the goal is try to find the position where x equals to 0. That's what you learn about Newton's method, right? So if you can just walk slowly from negative x until one day x equals to 0, that's the solution. That's one way, but that's not the Newton way, right? Newton is smart. Now, I'm going to tell you, you can actually use Newton's method to find the smallest point. So actually, for optimization, we usually want to find the smallest point. So actually, we want to find this point. This is the smallest point. Okay, the lowest point. So over there, what is 0? Anyone? Derivative. Yes. Yes, you're right. So how can we find it? Not that complicated. How about we take derivative of this and use Newton's law? Right? This is the original function. In the Newton's method you have learned, there's a trick to find f equals to 0. If right now I take the derivative, I have a new function, it's a f prime. I use Newton's method again. I will find f prime equals to 0. That should be the position right here. That's the trick. No, just derivative once. Just once. Just once. So the trick is, if you take derivative of the function once and use the Newton's method on that function, when you can find f prime equals to 0, that actually is the minimum point. If the function has a minimum point. Make sense? Yeah. So the problem is sometimes we don't know how the function look like. So we will use something that we use a lot. Another famous person, Taylor. Not Taylor Swift. Taylor expansion. There are 2 famous Taylor in the world. Okay. Some people said that Taylor Swift is another reason why America is strong. Okay, anyway, why do we use Taylor expansion? And also, why second order Taylor expansion? Because a second order function, if for f double prime positive, we have a function like this. There is a bottom point. So if you have a function that has a positive second order derivative, the function goes up and there is a bottom. So it's a problem you can find minimum. Okay? So if I approximate the function by third order Taylor expansion, I may have a function like this. Then sometimes I will find this point, sometimes I will find this point. And actually for third order function like this, where's the minimum? It's down there in the hell. Or the maximum is up there in the heaven. So We don't want third order Taylor expansion because it's difficult for us to find the minimum point. Use second order. As long as f double prime is positive, we should be able to find a minimum point. So that's the idea of second order Taylor expansion. So I'm not sure. I think you have learned this before in calculus, right? So this is the second order Taylor expansion. Once you have it, then follow this student just mentioned. I'll just say, okay, let's take a first order derivative and make it equals to 0. So from here, after you take the first order derivative, you have this function, and you force this to be 0. And there is some value you don't know, x you don't know. So you can derive x equals to x0 minus f prime divided by f double prime. So in Newton's method, actually you can iteratively find the solution right here. Iteratively. That means you can have an initial guess and try to solve for f prime and f double prime. Apply this function. It will tell you what is x k plus 1. It will tell you what's the next point. Okay? So I think it will be better if I give you one example. Six plus 7 minus 9. Okay. Can someone tell me what's the optimal? What is the optimal solution if I just give you this? So probably you can do some mind calculation, or if you don't know Newton's method, just trying to, okay, maybe I can change the form into a certain way, then I can find it. Okay, what Newton's method wants you to do is not to change the form. Just follow the procedure. You can find a solution. Okay, I can show you very easily. I have an initial guess. Random guess, 1. Okay? So what Newton's method said, I need to compute f prime of x and f double prime of x. Okay? So f prime, 12x plus 7. Plug in the first value. Okay, so it's 12 plus 7. It's 19. Okay? F double prime is 12. Okay, good. Follow Newton's method. X, k plus 1 equals to, so now k equals to k plus, I should say k plus 1. K plus 1. So k is 0. So now here is 1. Okay, so equals to whatever Newton said right there. Just follow. Don't believe in any other math. Just follow. Trust Newton. Okay, Newton said 1 minus, okay, 19 over 12. Okay. What is the answer? Just Google it. 1 minus calculator, 19 over 12. So 5833. Okay. Now do this one more time. Do this one more time. So if I do this one more time, this is my x1. I want to do this one more time, and then I need to compute what is f prime at this point. So f prime is this equation. So 12 times 5833 plus 7. Oh, negative. There's a negative sign here. So what is that? Use a calculator. 12 times negative 0.5833 plus 7. Okay, it's something very small, 0.0004. Okay? F double prime the same, which is 12. So I follow Newton's method. X2 equals to X1. X1 right now is this. This is X1. Minus first derivative divided by 12. So at the end, this is very small. At the end, I will get exactly same, almost the same solution. That's a solution. Almost the same. I just ignore it. Okay? So from here, did I use any mathematical tricks? Did I try to change the form or try to do something with it? No, I just follow. I just trust Newton's method. Just trust this equation. Make a guess, like your design. Maybe thickness use 3. Okay, the function probably is bending angle. Okay, so if you can compute first derivative of bending angle with respect to thickness, if you can have this value, and also second order derivative, then this is your initial thickness. This is derivative of bending angle, second derivative of bending angle. It will tell you what's the best thickness. But the issue is, how do you take a derivative of bending angle? Right? That would be the issue. How? Do you remember you will do some experiments? You may choose thickness and probably this angle, right? So at the beginning, you have a guess, maybe 3 millimeter. And this, you can say this is the max, largest bending angle, right? And you realize, okay, your design can bend 60 degrees. So you have 1 point, only 1 point. So next, probably you make a guess, you choose 4 millimeter. And then you realize, hey, really, I have a better angle, which is 65. Okay. Now, how about we try 2 millimeter? And then I realize the angle is like this. Maybe 62. Something like this. Okay? So probably the function looks like this. Probably the max angle versus the thickness of the wall is behaving like that. So if you have a function like that, you can take a derivative of this. You can even take a second order derivative if you have a function. Okay? So I'm going to show you something called finite difference. Actually, it's one of the slides later on. When this is written on the wall like this, you are scared of it. But if you get to understand what's going on, it's just something like this. Okay, I will let you know what's going on. This is so-called the delta x. Okay? This is delta x. So f prime can be approximated by actually this. This is what you said, limit, right? But this is the approximation of limit. Calculus. This is calculus. In calculus, we limit this delta to 0. We shrink it to 0. But in real life, we don't need to do it because it's impossible for you to find 0 delta. So just pick a small number. Maybe 1 millimeter is a small number. So in this case, this is your x. So this is your f of x. This is which one? F of x plus delta x. So in this case, actually, it will equals to 1 millimeter, and this value is 65 degree minus 60 degree. So you will have a slope of degree over millimeter. So for every increment of 1 millimeter, my bending angle increased by 5 degrees. That's the slope. That's your first order derivative. How about second order? The issue is how do you do second order derivative? It's harder, but it's not very hard. Okay, so it will use all three values here. This one is actually f x minus delta x. So actually it will be 1 millimeter is my delta square, and over here this is 65 minus 2 times the current one, which is 60 degree, plus this one, 62. Order derivative. So use this real example. Maybe it's easier for you to understand math. So probably you are doing this kind of optimization. You choose a design variable. You have an initial guess. You have some kind of function you want, but this kind of Newton's method finds you the smallest. So actually, you will find the smallest bending angle. But in our project, we want the largest. What do you do? Maximize a function can be converted to minimize the function, negative of the function. Okay. So maximize bending angle can be computed as minimize negative of bending angle. And you can only do minimization using Newton's method. Okay? So whatever I tell you right here, you are following minimizing something. But if you truly want to maximize something, put a negative sign in the front, then you will have minimizing negative of that method. Once you have minimization, you can apply Newton's method. It will help you to find the minimum point, like this example. Okay? So, time is up. My time is up. Any questions? I'm sorry, I have to shrink my introduction of design method. You need to have the mindset. You need to find the most appropriate variable. What's the function? Do I maximize it or minimize it? What are the constraints? Am I having too many constraints? Get rid of the non necessary ones. Can I try to solve by some mathematical problems, mathematical methods? If you don't use a method, that's okay. You are just randomly guessing your values. But there are systematical methods help you to find minimum point. Maybe you can try it. Okay. Homework. There's a homework. So here's the solution example. Here's the problem I give you. Different value set. Do this. The initial guess is the last digit of your phone number. Don't tell me you don't have a phone or you have a phone number. Just if your phone number ends with 9, then that's your initial guess. Try to solve this following what I did right here. The reason why I write it down here is because you need it for the homework. Solve this in 3 days, upload to the Google Sheet. You can write it down on piece of paper, take a picture, upload a picture. That's fine. You can type it down in Google Form. It's up to you. Okay? Any questions? No questions. That means you are excellent. So that's it for my lecture. Let's take a break. The next next lecturer will come. Is she here? Oh, outside? Why? Just come in. Okay, anyway, thank you for today. My job is done. Thank you.